Hello. Today I'm invited to talk about the PV-led engine project, which is a project about developing, characterizing, and dimensioning PV-powered lighting systems. And to give you an example of what this is about, it's about cable-free outdoor lighting. And there's some examples here with some various light posts in various scales, where you have from bike rails to rescue ladders to light at the beach. And within this project, we are a group at the DTU that have developed a world record efficient standalone system. So what are these? Today we are looking at high-end powered lighting systems, which in scientific terms are called light-to-light system. And what can they do? They are cheap to install. They are cable-free, so you don't have to dig up the streets to have lighting. They have very low operating cost. And in some cases it can give new lighting opportunities because it's cheap, it's simple, and you don't have to dig up cables. But there's also some challenges in these systems. First of all, there's a lot of energy conversion steps. First, the light has to be converted into electricity. It has to be stored right, and it has to come out as light. And all these energy conversion steps needs to be efficient, because otherwise there's not energy for the lamp. And you also have to focus the light where you actually need it and not all other places. And the energy management is crucial, and you can see in this chart, which I will elaborate later on, that if you have intelligence, you can distribute the energy and let the lamppost light all the night, though not with high power, but if you don't have it and just have a passive system, you will burn out the energy at full power during, say, 1 or 2 or 5 hours. So what does these systems consist of? First of all, there's a solar cell, but on top of the solar cell, there's some glue and some optics and some protective things, so the solar cell actually can sustain the environment. And there's some optical losses before the light hits the solar cell. Then the solar cell converts the solar light into electricity with some efficiency. And also the voltage levels of the solar cell and the battery is in general different. So you need a DC-DC converter to convert the electrical power from the solar cell into the battery storage. And also when you go from the battery to the LED or whatever light bulb you're using, you also need to convert the voltage levels. And then when you have converted the electric energy to light, you also need to pass it through some optics where it directs it, and there's also some losses in it. Then there's some sensors. And there's some pictures of the various parts of the system. And the downwards picture is an example of these systems. And from the optical part, here is another illustration of it. We have the light source, which is the sun. And there's some weather phenomena, location phenomena that create shades, local shades from building environment. There's a solar cell system, and there's an electronic system, where you have energy conversion in all places. And going the other way, we go opposite. We convert electric energy to light and pass the light through optics. And we are looking into optimizing all these subcomponents. We have also developed a mathematical model, so we actually can dimension these systems. Especially up here at these high latitudes, there's a large difference between day lengths at summer and winter. and also there's way less light in the winter than there is in the summer. And therefore, it's important to be able to dimension these systems right if you want reliable lighting based on these systems. And here is a screenshot of the mathematical model where we either can validate it by using measured data and measured weather data and solar data, or we can take what is called typical meteorological year, which contains information about the weather and the solar radiation at the specific place, and use this as a model tool where we, in a time-resolved manner, can go through, I think we use time step of approximately 5 minutes, what is the energy flow in the system, which is a very strong tool in order to create this reliable lighting in the city environment. And we have also developed laboratories so we can feed in data from the measured components. We can measure the batteries, we can measure the solar cells, we can measure the LEDs, and we can also measure the electronic conversion efficiency. We also have weather stations, and we have a special camera that can measure shade, and all this is feeding into this mathematical model and help us improve and being able to simulate prototypes. Then we can test them on the field externally and at DTU where we have external logging on it. And again, for this system to work, it's important to use the energy intelligent. So lighting with a low power all night instead of lighting with a high power a few hours. So together with especially Electro, in this project, we have developed a world record efficient electronic controller for these systems. And further, we have established laboratories so we can test all the components, the solar cells, the LEDs, the battery, and the electronics. And we have made some prototypes, as you can see. So at Roskilde, we have a very good LED competences where we can test LEDs, light-emitting diodes. We can make a spectral design. So we have the right color temperature, we have the right colors, so the light feels nice. And we can do optical design, test and model it and fabricate it. And do some thermal model, make it into circuit boards, and actually create a LED system. Here is a picture of a so-called near-field goniometer we have at Roskilde, at Risø, that actually measure the spatial distribution of light sources, which is very helpful in order to optimize the optics and the luminaires. And this is a sphere that can measure the total luminous flux of LED, which is also present at Risø and very frequently used. At Risø, we also have a photovoltaic research where we start by the solar cells, test the solar cells, put it into some optical systems. We can actually also do our own solar panels. We can also test the solar panels. We can test the full electronic system, and we can put it out on the field where we have advanced measurement equipment to measure all details of the sun and the weather. And then we put external logging on it, so we know what's going on in the system. One of our collaborators had a case where he was asked to provide or bid in with some lighting, standalone lighting systems for a place in Saudi Arabia. And there's a picture of the system with the solar cells horizontally and the LED panel mounted vertically. And there was actually a request of almost 1,000 of this in this new area for this King Abdullah, where they just want to have a very, very nice area. More pictures. And this private company made a concept with the Norwegian architect Snøhætter in 2009. And together with DTU Photonics and other institutes and companies, we finalized the design in last spring and actually made a very nice luminaire. Here's an example of the PV panel, which is 18 volts and 24 watt peak. And we use this to gather weather data from Saudi Arabia, calculate the details of the and figure out how much energy is actually available from the panel. We also needed a battery, and we made this model, and you can see in the table to the left that we are only using 20% of the battery capacity, and that actually enables the battery, since there's one cycle per day, to last almost 10 years. However, this is at room temperature, and the temperatures in Saudi Arabia is way higher, so we expect the lifetime of the battery to be 5 years in this case. And we also developed a very good reflector for a LED luminaire and the LED luminaire, where we had developed the reflector, so we got the light exactly where it needed to be. And here is our reference luminaire, commercially available luminaire, the light distribution of it. To the left and to the right is what we developed. And you can see the old luminaire is having a very narrow distribution, and the new luminaire is having a wider distribution and distribute the light downwards where we actually want the light to be. Here's other illustrations of it. This is the old luminaire, and please note the scale. It goes from up to 10 lux, and with the new, we actually got up to 50 lux for the same current, for the same energy. And here you can see with the new luminaire how much light do we get in this. These systems were supposed to make paths, so there will be some walls on each side, and then they will be lighting into the street or the path. And here you can see the light as a function with the months on the other axis, and we have more light than what was required in all times of years of the year. And we also measured it, and it actually turned out as we simulated it. And again, back to this intelligent use of energy. One example of distributing the energy is to divide the day in phases, where of course when there's daylight you don't use energy, and from sunset to some point in the evening you are using you're illuminating with a high power, and then you dim the LED throughout the night in various phases, and just before sunrise you increase the light level again. And therefore you actually use the energy when there's people, and people actually can enjoy the light, and use less energy when it's dark and there are fewer people. And here you can see how we thought that the phases could be distributed throughout the year in order to make sure that there's energy enough. And here we calculated the energy balance, and you can see as the energy provided from the solar cells is higher than the energy required from the LED. This is a reliable lighting system that will light 360 days a year for this location. And we have measured the efficiency of the charger, and you can see this charger is optimized for Saudi Arabia because the higher the temperature, the more efficient the charger is. This is something we can optimize more. And also, LEDs works most efficient under low power, under low current. So more LEDs that is each operated low give more light for the energy, which we are also using here. So to wrap up, I hope I have introduced you to this PV-powered lighting and introduced you to the opportunities, challenges, and briefly about the technology. We have walked briefly about the characterization of them, how to dimension, and I have showed you a case study. And if you know more, want to know more, we will have a conference on smart city lighting and PV-powered lighting in the Bella Center on March 19th. And you can look at the program here. And if you're interested, please sign up.